Well, hello, Math 160 students. After our class today, I thought that because related rates can be kind of a challenging topic and yet a fun one, it might be worth doing another example for you so you have another illustration of this process. Of course, once you've watched this example and you go back and maybe look at the group work again that we did today, at that point you might be ready to try the homework. If you get stuck on that, of course, feel free to come to my office hours, go to the tutoring center. Definitely try and get things cleared up if the homework is giving you a hard time. But anyway, I wanted to do another example with you, and this time, this one is a little harder than the ones that we did earlier, only because there's sort of less numerical values just sort of staring right at you in the problem. So that means that we have to sort of figure out some of those things for ourselves. Let's read the question, and I apologize if there's a glare on this board. It's not the cleanest board in the world either, so bear with me, but I can read this for you here. This says, a lighthouse is located on a small island 3 kilometers away from the nearest point P on a straight shoreline. Let's stop and make sure we understand what that is saying. So there's a lighthouse, and there is a straight shoreline, and 3 kilometers is the distance from the lighthouse to the closest point on that shoreline. Okay, and that light makes 4 revolutions per minute. Okay, so it goes around 4 times, circulating through 360 degrees 4 times. Except that, as we talked about in class today, we really shouldn't use degrees when we're measuring these angle values. So what we're going to do is convert it into radians. 4 revolutions, of course, is going to be 8 pi radians. Right? So every minute, this light travels through a total accumulated distance of 8 pi radians. Okay? Question is then, how fast is that beam of light moving along the shoreline when it is 1 kilometer from P? So the light, of course, swings around and shines a light right on that shoreline. And we want to know how fast that light is moving at a particular time. Okay? So do you remember our process for solving these problems? We have a procedure with those 7 steps. And the first one is to draw a picture. So we're going to try and draw a picture here. And I think the natural thing to do would be to draw the straight shoreline. The shoreline here. And then up here is this island where we have this revolving light that is shining on the shore. So this distance right here is supposed to be a straight distance of 3 kilometers. Right? Okay, so we know that much. What we need to do is take the picture then and label it with the variables that are going to be important in this problem. So for one thing, we need to have a good knowledge of this distance here, because it talks about, I'll call it x. Okay, I'll use x for that. Because we're talking about the distance between some point on the shoreline and P. By the way, this is P right here. P is that point where the shoreline is closest to the light. Okay? So I'll call that x. And the other thing that we were given information about is the angle. So I'm going to label the angle here as theta, like that. Okay? So we have some labels on the diagram now, which is the second step in the process. The third step is to try and write down what it is that we're trying to find. So what we want to find, let's just read the last part of the question to remind ourselves, how fast, in other words, at what rate of change, is the beam of light moving along the shoreline when it is 1 kilometer from P? So that's just asking for the rate of change of x, right? Because x is measuring the position along the shoreline. The rate of change of that, which is really the speed of the light, in other words, how fast is the speed. That speed is what we're trying to find. And we want to find it when what? When x is equal to 1, right? The distance should be 1 at that time. Great. Okay. So what are some of the things that are given here that we do know? Well, obviously we know that the light makes, of course I already talked about the 3 kilometers. The light makes 4 revolutions per minute. That really just means that every minute, I guess I'm going to measure time in minutes in this problem, okay? The rate of change of the angle with respect to time would then be 8 pi, right? 8 pi. And we're measuring it in radians right now, okay? It's radians. Great. So we know that. So we have a rate that we are aware of. We have a different rate that we're trying to find. So the next step in the process, of course, is to try to write down a relationship between the two variables that are being related. So the x and the theta. So you have to look at the picture and ask yourself whether you can come up with a relationship between the variables that you see here. Okay? And this is almost always a geometry consideration. So in this case, the theta is giving me an angle in this right triangle, and so the two legs of that triangle are x and 3. So what we know then is that we know, I guess I'll just write it that way, we know that the tangent of theta is x over 3. Okay? And both theta and x are functions of t. Perfect setup for the chain rule, and that's exactly what I'm going to use right now. I'm going to take the derivative of both sides of this with respect to t. That is our 6th step. We're already up to the 6th step. Okay, the derivative of tangent, because we're measuring theta in radians, we can freely use the standard value for the derivative of the tangent, which is the secant squared of theta. We multiply that by the derivative of theta with respect to t, which of course we are going to be able to plug in. And on the other side of the equation, we have a constant 1/3 times dx dt, which is the rate that we're trying to find. Okay? So we kind of know what we need to put in for d theta dt. What about the secant of theta, which is being squared here? We can come back to this triangle. Remember that we're trying to find the x dt when x is equal to 1. Well, when x is equal to 1, we can actually figure out the hypotenuse of this right triangle as a length of square root of 10 kilometers. Okay? And the secant is just the reciprocal of the cosine function. So the cosine here would have been the adjacent over the hypotenuse, 3 over radical 10. So the secant, therefore, is radical 10 over 3. So let's just plug that in. Radical 10 over 3 squared times 8 pi equals 1/3 of dx dt. Okay? So let me just give myself a little bit more room here now that the beauty of the video is you can always go back and remind yourself what was there. Just rewind the tape a little bit. But anyway, I can now find dx dt quite easily. Square root of 10 over 3, when I square it, gives me 10 over 9. And then I have an 8 pi. I'm going to put a factor of 3 in there by moving the 1/3 over. So this comes out to 240 pi over 9, which we could reduce, if we wanted, by dividing 3 by 3. 80 pi over 3. And that would be in what units? You have to come back and remember this is the x dt, so that's the rate of change of the distance along the shoreline with respect to time. So that would be in kilometers per minute in this case. Okay? So there wasn't a lot of numerical value given in the statement of the question, but if we just simply draw the diagram and start labeling it, going through the procedure that we talked about in class, we can eventually see how to put this whole thing together using the geometry and using what we know about derivatives. So just wanted to give you another example to kind of show you yet another practice problem that you can try and make sure you understand. And if there are any questions about it or anything that we did in class today, feel free to talk to me during my office hours or send me an email. I'll try and get you straightened out. So, okay, thanks for watching, and we'll see you soon. Thanks.